Hello everyone, I'll be presenting my project, Creating Tileable Textures Using Diffusion in Painting. In the realm of computer graphics, a technique that's typically used when applying an image to a surface is tiling. This means that the same image will be copied over the whole surface. For pictures which are designed to do this, the result looks very clean. For other pictures which are not designed to do this, the result looks very obvious. My project will focus on a new technique that allows one to create a tileable texture from any image. We start with an input texture we want to make tileable, then break it up into 4 chunks. We then rearrange these chunks like so. Turns out, I am not the first person to discover this rearrangement. In my research, I actually stumbled upon this patent from Pixar. Checking how this new image tiles with its neighbors, we can see how the image now tiles seamlessly with the images around it, just not with itself. To solve this problem, I trained a diffusion inpainting model on texture data, which can be used to fill in this area here. This will theoretically make an image which will tile cleanly. For the model, I used approximately 65,000 samples from several databases. I used a 95/5 training val test split in order to maximize the amount of training data. To pre-process the texture, I cropped the image down to a square aspect ratio, then resized them to 256 by 256. When training on a texture, I decided to use a standard technique of applying a random mask of rectangles. The random masks are useful since they help to prevent the model from overfitting, since the model sees a new mask every time. You can think of this as a somewhat janky way to increase the number of training samples that are available to the model during training. In my research, I found that the best model for diffusion inpainting is currently a U-net. I customized my own U-net with approximately 120 million parameters, which my research told me was roughly the number of parameters needed to perform diffusion on the sizes of images that I was working with. For training, I decided to keep the learning rate deliberately small. I did this even though it might impact how long it took the model to learn, because from my research I knew that the diffusion process is mostly learned in the later stages, where a small learning rate would be beneficial. The optimizer and batch size were both chosen based on existing research, but the batch size was heavily influenced by the amount of resources that I had on hand. The loss curve followed the expected behavior, and that it originally dropped off substantially. However, the loss remained remarkably consistent later on. This is when the model entered the later stages, where the low learning rate was really crucial. Because the model was still improving during this time, the details that it was now learning were very, very small. And I was worried that large changes to the weights of the model during this stage would make training either intractable or just take way longer than it would when using a low learning rate that would be more careful. Early results indicated that the model was essentially just picking up the sample mean for each image and just putting one solid color. However, later and later stages showed that it was actually learning the overall diffusion process well. We can now see the results of the model and see if the produced image does actually tile cleanly. So it's not quite perfect. If you look closely, you can see some artifacts. However, this is much better than the alternative. There are some images where the algorithm doesn't perform as well on. That's just based on the nature of the image. Sometimes the algorithm can't really stitch it together as well. However, for most images, the algorithm actually performs very well.